Hello everyone, welcome to the third video on algorithm analysis, and what we're going to be covering in this one is going to be the experimental studies of an algorithm. So to do so, we just pretty much have to follow three steps. The first one is to write the algorithm into a programming language, then run the program with different input sizes, and finally see how long each one of the inputs is taking and plot the results. So it should be fairly straightforward. So to do this, we're going to use one algorithm. We're going to use three algorithms that do the same thing. And we talked about this in a previous class, which is the problem of adding up consecutive numbers. So suppose you're trying to add up 1 plus 2 plus 3 plus 4 in all up to the end value, and n would be any natural number. So one way of doing so, it would be, for example, the algorithm A, which is using a for loop that goes from 1 to n and add up the value of I in each iteration. The second algorithm that does exactly the same thing is using a double for loop, and the third algorithm is going to be using the formula for the addition of consecutive numbers. So in all of the cases, they are doing the same thing, but each algorithm will have a different efficiency, and that's exactly what I want to have a look at. I want to see which one of these algorithms is going to be better. So to do so, I have given you in the pre-class code a little bit of a program there that you can actually you can use yourself. So the first thing that we're going to do is understand the code that I've given you in there. So we have three variables there called start time, stop time, and elapsed time. And then I have a variable of the type date that I'm calling current. So let's take a look at this. So there is a for loop that starts with I being 2000, I is smaller than 200,000, and I increases in steps of 2000. So the first iteration is going to be 2000, then 4000, then 6,000, then 8,000, then 10,000, and it's going to do that as many times needed to reach 200,000 times. Okay, so the next thing is inside the for loop, I am calling. The first thing I'm doing is I'm creating a new instance of the date class, which will give me the current date and time. But I'm actually looking at the current time, and then I'm defining a variable called start time, which is the time of the current time object. Then I'm calling an algorithm A method that we'll see in a second, and then I'm calling again a new instance of the date to get the current time. So if you see what's happening in here is I'm saving the time before the algorithm is running and then the time after the algorithm is running. And then my elapsed time would be the difference between the two of them. Now I'm doing that 3 times. I'm doing algorithm A, then I'm doing algorithm B, and then I'm doing algorithm C. So those three algorithms, those three methods are empty methods, and that's where we're going to write our algorithm. So we're going to write their algorithm A first, then algorithm B, and then algorithm C. Now at the moment, the three methods are empty, so let's take a look at what happens if I run this program. So when I run it, I get something like this. So we can see that we're getting a table that is showing me for different values of n how much time has elapsed during algorithm A, algorithm B, and algorithm C. There is an algorithm D there, but you can just ignore that. What we get in there is all zeros because it doesn't take any time to run those algorithms because those methods are empty so far. So the first thing we're going to do is we're going to go one by one each one of the algorithms and write the code in there. So let's start with algorithm A. So algorithm A is going to be So I need a sum variable, and I need a for loop that goes from 1 to n and just add up. So let's go and do that. So I'm going to need an integer sum that is equals to 0, and then I have a for loop that goes from integer I equals 1, I lower than n. Actually, it should be lower or equal because we're going from 1 to the actual value of n. And finally, I plus plus. So sum is going to be plus equals the value of I. Okay, so what we can see there is that this algorithm is adding up consecutive numbers from I to n, and is saving the result into a variable sum. Now I'm not plotting the actual result, but what I really want to see here is how long this algorithm is going to take to run. So I'm going to run it. Let's see what we have. So we can see that in this is the algorithm A. I have 0, 0, 0. I have 1, 1 in here, but all in all is 0, 1, 0, 0, 0, 1. So it really is a fast algorithm. It's not really taking that long, not even for the biggest number. Even for 200,000, I still getting a 0 in there. Now, some of you may ask, well, why, Amilcar, am I getting a 1 millisecond there? Well, because it's taking a little bit longer than just 1 second. So remember that when it's doing the subtraction, it's rounding up or down, depending on the cases. So it's not an exact kind of science. However, it will kind of tell you in what order of time this is actually running. So let's take a look at the second algorithm. So the second algorithm would be, I still need a sum, a variable sum that is going to start in 0, and I'm going to have 2 for loops. In the first for loop, I'm going to add from 1. I'm going to go from 1 to n, but in the second for loop, I'm going to go from 1 to I. And in this case, I'm not going to be adding the value of I, like in the case before. I'm going to be adding 1 each time. So this is doing exactly the same thing. So let's say here, int sum is equals to 0. Ooh, perfect, equals to 0. Then I'm going to have a double for loop. In the outer for loop, I'm going to go int I equals 0, actually starting at 1, I lower or equal than n, I plus plus, and in this case, we're going to go int j. I need a second variable that goes from 1 as well. But in this case, j is going to be lower, equal, or lower than I, and j is going to grow plus plus. Now, in this case, sum is not going to be added plus the value of I is going to be added plus 1. So this is doing exactly the same thing as the other one, but it's just another way of writing this code. If you have any questions with this code, please let me know in the live session. Now I'm going to run this and see what happens. Now something that we can see in here is that as the values start increasing here, 3, 12, and out of sudden start it drops to 0 again. Now we'll discuss that in a second, but what that is telling me is actually this second algorithm is taking a little bit longer than the first algorithm. Now these results are not exact. I have to run this a couple of times, so we'll discuss that in a little bit. Now let's go with the third algorithm, which is applying the formula. So the third algorithm would be the formula sum is equals to n times n plus 1 divided by 2. So int n is equals sum is equals to n multiplied m plus 1, and then this is going to be divided by 2. Now I should have another bracket in here. What's the problem here? So there it is. So I'm just casting this to an integer number so I can put it in there. And I'll run this algorithm again. Now, let's take a look at these results. So if I run it a couple of times, something that I can see is that the results are not being consistent. So if I run it one time, I get some sort of result, but if I run it again, I don't get exactly the same thing. Well, this is because this is experimental. The same thing happens in all of the science disciplines. So for example, if you're measuring things like gravity acceleration, these errors in calculation happen. And that happens because the models that we're working with are not ideal. My computer has certain characteristics that are not realistic. So for example, I'll give you an example. At the same moment that my computer is running these algorithms, it is also recording this video. So there is a lot of things that the computer is dealing with at the same time, and that's why the performance of that algorithm is not always the same, is not consistently the same. However, there is something that we can see consistently in here, that my first algorithm, it always takes more or less between 0 and 1 milliseconds. It doesn't take any longer than that. Well, there is one example in here in which it's taking 15 milliseconds. But if you think about it, that might be because at that time, the computer was dealing with something else. So that one wouldn't be a significant sample. Probably exactly at that time, the computer would be handling, I don't know, something on the internet, or the computer would be handling something with my headset or whatever it is. But let's take a look at the second algorithm. All in all, I have more results that are slightly bigger than in the first algorithm. So I have a 6, I have an 8 in there, I have also a 13 in there, I have a 4. So all in all, as a thumb rule, I can say, well, my second algorithm seems to be taking a little bit longer than the first. And the third algorithm is always taking 0. So I can see that my third algorithm seems to be the fastest one of all of them. So I'm going to run it a little again just to see that that is actually more or less consistent. Again, I have the odd 4 in here, but I would never have something like a 15 in this first column. In this case, again, it's fairly fast, but I have an 11 here. And then in the third one, it's always 0. So that is fairly consistent in there. So something that we can see there, guys, is that these algorithms, I can see there that these results that I'm getting experimentally are consistent with what we saw in the practice, in the theoretical part, sorry. So in the theoretical part, we saw that the complexity of this algorithm is O(n), because the complexity, the algorithm happens n time. However, this one has a complexity of n log n, because it is a little bit worse than log n, but it's not as bad. It is a little bit worse than O(n), but it's not as bad as O(n) squared. And in this case, this is always constant. So this mathematical operation will always take the same amount of time regardless of the size of n. And it could be anything, and I'm getting always the same value. So the best of these 3 algorithms is actually the last one. So one of the things that we need to keep in mind is that these experiments although they're fun to do, they have their limitations. And one of the problems that I have, for example, is that my computer is a very strong computer, so I don't see any, even the most complex algorithms seem to run very quickly and really fast. So for us to measure how good is an algorithm using an experimentation platform might be a little bit of a problem because my computer, because it really depends or relies on my computer. So if I have a slower computer, then definitely I see those differences a little bit better. But if I have a faster computer, then the computer is going to affect the results that we are seeing in there. So whether the algorithm is running quickly in a computer doesn't mean that the algorithm is good. That's one of the limitations that we have with the experimentation. So if I want to compare two algorithms, I need to make sure that they run in the same hardware. That's exactly what I did. In this case, I put the two algorithms and I run them in the same computer. However, that doesn't mean that the results are always going to be consistent, because those results depend on the circumstances in which the computer are at the moment. So if the computer is under particular stress because of running any other process, then that result might not be reliable or consistent. So those are the kind of things that you need to keep in mind. Brilliant. So that would be it for this last video, and I'll see you. Thank you very much for watching, and I'll see you in the live section. If you have any questions, just let me know in the live session. All the best.